Right now, there are objects in the universe so powerful that if one appeared where the moon is, every living thing on Earth would die in under a second. Not from heat, not from explosion, from the simple geometry of space itself folding. And here is the part that should stop you cold. You are already inside that geometry. Every moment of your life, something is bending the fabric of reality around you. You call it gravity. You have always called it gravity. A force that pulls, a thing that drags you toward the floor when you stumble, holds the moon in its orbit, keeps the oceans from drifting off into nothing. But what if gravity is not a force at all? What if nothing is being pulled? What if the reason your feet stay on the ground is not because the earth is dragging you down, but because time itself is moving slower beneath you? That question is not philosophy. It is not speculation dressed up to sound dramatic. It is the backbone of the most tested, most precise theory in the history of science. And by the end of this, you will never look at the floor the same way again. Because the thing keeping you here is not a force. It might be a current, and the current is time. In 1959, two physicists at Harvard pointed a gamma-ray detector at the roof of a building. Then they pointed another one at the basement. Same building, same city, same moment. The only difference was 22 meters of height. And what they found rewrote the architecture of reality. The physicists were Robert Pound and Glenn Rebka. They were trying to prove something Einstein had predicted 44 years earlier. Something so strange that even Einstein spent years second-guessing himself. The idea was this time does not pass at the same rate everywhere. The closer you are to a massive object, the slower time moves for you. Not metaphorically, not in some abstract theoretical sense. Physically, measurably, verifiably slower. Pound stood at the top of Jefferson Tower at Harvard University. Rebka stood at the bottom. Pound sent gamma-ray photons, little packets of light energy, downward. And here's the thing. By the time those photons reached the bottom of the building, they were measurably different. They had been blue shifted. The frequency had changed. Not because of speed, not because of temperature, because the photons had traveled from a region where time moved slightly faster into a region where time moved slightly slower. And that difference showed up in the light itself. 22 meters, the height of a two-story house, and time was measurably different between the floor and the ceiling. The experiment worked. Einstein's prediction was confirmed to within 10%. Later versions of the experiment got it to within 1%. This is not a theory anymore. This is a measured, confirmed, repeatable fact. Time runs slower near the ground than it does near the roof. Now hold that thought, because it is about to get much stranger. Here is what Einstein actually said about gravity, and almost nobody phrases it this way. He said that space and time are not two separate things. They are one thing, a fabric. Physicists call it spacetime. Picture it like a rubber sheet stretched out flat. Now put a bowling ball in the middle of that sheet. The sheet bends. It curves downward around the bowling ball. That curve is what we call gravity. The Earth curves space-time around it. The Sun curves it even more. A black hole curves it so severely that the geometry closes in on itself. But here is where the metaphor breaks open into something genuinely strange. It is not just space that curves, it is time. And this is the part that changes everything. When time curves near a massive object, it moves slower. You standing on the surface of the Earth are in slightly curved space-time. Your feet are deeper in that curve than your head. Right now, as you watch this, the clock in your feet is ticking fractionally slower than the clock in your head. Your head is aging faster than your feet. The difference is tiny, about 90 nanoseconds over a lifetime. But it is real, and it is verified. But here is the pivot, the real pivot. Because if time runs slower near mass, then there is a gradient, a slope in time. Your head is in faster time. your feet are in slower time. And Einstein's geometry says that everything in space-time follows the path of least resistance through that gradient. Not because it is being pulled, because it is trying to take the straightest possible path through curved space-time. Think of it this way. Imagine you are driving across a curved hillside. You are not steering. You are just going straight. But the hill is curved, so straight on the hill still curves you downward. You are not being pulled. The geometry itself is sending you that direction. That is what gravity is. Objects are not pulled toward mass. They follow the straightest possible path through a space-time that mass has bent. You are not being dragged to the floor. You are following the geometry of time itself. The floor is in the direction of slower time, and the universe, in a deep and strange way, is always moving toward where time is slowest now. If that idea is still sitting comfortably in your head, wait, because black holes are where this stops being abstract. A black hole is what happens when mass is so densely packed that it curves space-time completely. Not a little bit, not like the Earth curves it completely. At the edge of a black hole, a surface physicists call the event horizon, the curvature of space-time becomes so extreme that the direction toward the center becomes the direction of time itself. Not a direction in space, the direction of the future, which means that once you cross the event horizon of a black hole, falling inward is not a movement in space. It is a movement through time. It is forward. It is the only direction available. You cannot stop falling any more than you can stop experiencing the future. The black hole does not grab you. It simply makes falling into it the only temporal direction that exists. Nobody comes back from that. Not because the black hole is stronger than you, but because the future does not have a reverse. And the strangest thing in this entire video is still ahead. In 1974, a physicist named Stephen Hawking sat with a calculation that was supposed to be routine. He was combining quantum mechanics, the physics of the very small, with general relativity, the physics of the very massive, and the math handed him something impossible. It told him that black holes glow, that they slowly, over almost incomprehensible timescales, emit radiation and lose mass, that they eventually evaporate, not explode, not collapse further, evaporate like a puddle of water on a warm day. They simply thin out and disappear. This takes longer than the current age of the universe for a typical black hole, but the implication is enormous, because if black holes evaporate, then all the information about everything that ever fell into them, every atom, every particle, every memory of every star that collapsed, that information goes somewhere. Or it does not. And if it does not, the universe has just committed a crime against physics, because quantum mechanics says information cannot be destroyed ever. The arrangement of particles might scatter, might disperse across billions of light years, but the information encoded in them is supposed to be conserved forever. That is a law, not a guideline. A law. But Hawking's calculation says black holes radiate purely randomly. The radiation coming out carries no record of what went in, which means the information is lost. Which means one of these two pillars of physics, general relativity or quantum mechanics, is lying to us. This is called the black hole information paradox. It has been unsolved for 50 years. The sharpest minds in theoretical physics have thrown everything at it. String theory, holography, firewalls, fuzzballs. None of them fully work. We are sitting at the collision point of the two greatest theories ever devised, and they cannot both be right, and we do not know which one breaks. Somewhere in that breakdown is something new, something we do not have words for yet. But here is where the curve tightens. Here is where the idea of time as gravity becomes something personal. If time flows faster where gravity is weaker, then something at a great distance from all mass, far out in empty space, experiences time rushing forward at its maximum rate. And something sitting deep in a gravitational well, near a neutron star, near a black hole, experiences time nearly frozen. 1 second for them might be centuries elsewhere. This is not metaphor. GPS satellites orbit about 20,000 kilometers above the Earth. The weaker gravity up there means their onboard clocks tick faster than clocks on the ground, by about 38 microseconds per day. That is a measurable, real difference. And if engineers did not correct for it, your GPS would drift by about 11 kilometers every single day. Time dilation is already embedded in the technology in your pocket. You are already living inside relativity. You just did not know it was time making you heavy. Now here is the turn, the one that reframes everything. We have been thinking about gravity as something the Earth exerts on you, a force flowing outward from mass, reaching across space, grabbing you. But Einstein's geometry says the opposite is true. Mass does not send anything out. It just exists, and its existence bends the space-time around it. You are not being acted on by the Earth. You are both sitting inside the same curved geometry. The Earth curves the geometry more because it is more massive, but you curve it too. Every proton in your body bends space-time by a fraction so small it is almost unmeasurable. Almost. You are not a passenger in gravity. You are a participant in it. Your existence is in a technically real sense warping the fabric of the universe. Slightly, invisibly, permanently. And that leads somewhere almost unbearable to think about. If every mass in the universe bends space-time, and if space-time is one continuous fabric, then every object in the universe is connected through that fabric to every other object. Not through a signal, not through a force carrier, through the geometry itself. The sun's gravity reaches Pluto not because it sends something there, but because the sun's mass curves space-time all the way out to Pluto and beyond. And Pluto sits inside that curve whether it knows it or not. Pull back further. The Milky Way bends space-time on a galactic scale. The Virgo supercluster, a structure containing more than 1,000 galaxies, including ours, bends it on a scale you cannot picture. And yet, at the very largest scales, something is fighting back. Dark energy, a name physicists use for something they cannot identify, cannot detect directly, and cannot explain. What they know is this: the universe is not just expanding, it is accelerating. Galaxies are moving away from each other faster and faster, not slower and slower, the way gravity should be making them. Something is using space-time itself outward, something with negative pressure, something that fills empty space, something that grows stronger as space expands. We know it is there because we measure the expansion, and the math demands it. But we do not know what it is. It makes up roughly 68% of everything in the universe. The thing we understand least is also the dominant ingredient, which means most of the universe is beyond our current physics, completely. And here's the thing that should make you feel both very small and very strange. If space-time can be bent by mass and stretched by dark energy, then space-time is not a rigid stage. It is not a container the universe sits inside. It is something more like a substance, a medium, something that can flex and warp and tear and carry ripples. In 2015, 2 detectors in the United States felt space-time itself ripple past them. These were gravitational waves, predicted by Einstein in 1916. 2 black holes, a billion light-years away, had spiraled together and merged. The collision released more energy in that final fraction of a second than all the stars in the observable universe produce in the same time. And the ripple from that merger, a tiny stretching and squeezing of space-time itself, traveled for 1 billion years across the cosmos and made the detectors at LIGO twitch by a distance smaller than 1,000th the width of a proton. That is the measurement. 1,000th the width of a proton, across a detector 4 kilometers long. And they caught it. Humanity built something sensitive enough to feel the geometry of the universe vibrate. There is no way to prepare for what that actually means. Space-time rang like a bell, and we heard it. So where does that leave you at 11 at night with the floor beneath your feet? The floor is not pushing you up because the earth is strong. The earth is curving time downward beneath you. And you, like every object in this universe, follow the gradient of time the way water follows a slope. Not because you are forced, because the geometry has no other option for you. Down is the direction of slower time, and the universe is always falling that way. And if you find that beautiful, if you feel a strange, quiet vertigo at the idea that what you have always called weight is actually a relationship with the shape of time, then consider what it means. Every moment you have ever felt the ground beneath you, every time you fell, every time you caught yourself, every time you felt heavy with something you were carrying, you were not being pulled by a force. You were following a curve in the fabric of time. You were tracing the geometry of a universe that bent itself around a rock 4.5 billion years old so that life could cling to it. Carl Sagan said, "We are a way for the cosmos to know itself." The universe made creatures who can stand on a curved geometry and ask why they can't float, who can build instruments to hear space-time shiver, who can trace the equations all the way back and find that the thing they called gravity was time wearing a different face. And here is what nobody tells you. That face is still changing. The universe is not done. The geometry is still bending. Whatever dark energy is, it is winning. Space-time is stretching faster every second. In 100 billion years, the galaxies we can currently see will have accelerated so far away that no signal from them, no light, no gravitational wave, nothing will ever reach us again. The observable universe will be smaller. The evidence of everything beyond will be gone. A civilization born then, looking out, will see only darkness and conclude they are alone in an infinite void. They will be wrong, but they will have no way of knowing that. The universe will have hidden its own history. The geometry will have stretched the evidence beyond any possible recovery. What does that mean for what we cannot see right now? If time runs slower near mass and faster in empty space, and if the universe began from a single point of infinite density, where time itself may not have existed in any recognizable form, then the question, what came before the Big Bang, might not be a question about an earlier moment. It might be a question about a place where time had not yet invented a direction, where before and after had no meaning. The question might be grammatically valid and physically empty at the same time. Time did not begin when the Big Bang happened. Time might have been something the Big Bang made. And if time is something that can be made, then whatever made it was not inside it yet. Whatever came before was not in time, which means causality. The idea that things happen because earlier things caused them may not apply. The universe may have begun without a cause, not because it defied logic, but because logic requires time, and time was not there yet. Sit with that. Really sit with it. The floor beneath you is not solid certainty. It is a frozen wave in a geometry that did not always exist. Your weight is a clock running slow. Your future is the direction the universe is always falling. And the whole architecture of everything you have ever stood on was assembled by a process that began before was even possible. If gravity is not pulling you, but time is curving beneath you, then what exactly are you standing on?